fundamental theorem of calculus. Moving right along. Okay, fundamental theorem of calculus is really a two-part deal. The first one has to do with our antiderivatives. You'll notice this is different than what we've been looking at because I have an x in my limits. I have a variable in my upper limit here. Okay, so if you have a function whose integral is from a constant up to a variable, f of t dt, where f is continuous and x is somewhere between a and b, then our function would just depend on the value of x. So it's basically a formula so that if I give you an x value, you would be able to calculate that integral. Okay, so it's like finding a formula. In terms of a graph, when I give you the x value, an integral is like measuring the area under a curve. So if I am trying to write this g of x equation, I'm basically just getting a formula so that I could calculate the area under the curve at any given point. So I might want to calculate here, and then here, and then here. So instead of redoing the integral each time, we could just come up with a generic formula with x in the limit. So first I just want to talk about, in practicality, what this is actually referring to on our graph. So if this were the function, I want to find all of these things. G of 0, 1, 2, 3, 4, and 5. Okay, g is just this integral from 0 up to that number. So g of 0 means you have the integral starting at 0 and ending at 0. So what's the area under the curve if you don't go anywhere? 0. So g of 1. If I start at 0 and go up to 1, I'm talking about this area. What would you approximate that as? Probably about 1, wouldn't it be, if we just took this little triangle up here, it about fills in that one, so 1 box. So when I want g of 2, I already know from here to here is 1. How far is it from 1 to 2? 2, so altogether our area then would be 3. Okay, so g of 3, we have to figure out what does that part add in. 1.5, so now we're up to 4.5. Now is this exact? No, we are estimating, but we can get a general answer. G of 4, what's going to happen now? Right, this is a negative 1.5 approximately, so what's my area now? It's back to 3. It's like subtracting that amount off. G of 5, how much would I have to subtract off again there? It's another 1.5 off, so we end with a total area of 1.5 because areas above the x-axis are positive and below are negative. Okay, it asks us to also sketch a graph of this. So I put, I think, a grid on the next slide. G of 0 was 0, so we're just going to plot these points. G of 1 was 1. We had 2, 3. We had 3. We had 4. Back down to 3 and 5. 1.5. Okay, so this is my rough estimate of that integral, the graph of that integral, talking about the area under that particular curve. All right. So the actual first part of fundamental theorem of calculus is pretty cool result. It tells us if we have a function like this, its derivative is just f of x. Okay, so if I have an integral where x is in the limit we know an integral is an antiderivative, so an antiderivative and a derivative should cancel one another, right? So if I did the derivative of this, the only thing that changes is this x just becomes a variable in my function. Otherwise, it just drops everything else out. So knowing that, let's find this one. We're going to do it two different ways. The first way, I'm just going to do the fundamental theorem of calculus, do what it tells me to. Second way, I'm going to work it out by hand just to show you that it is in fact giving us the right answer. If I wanted the derivative of this interval, so option 1 is just using FTC, fundamental theorem of calculus. The fundamental theorem works as long as we have a continuous function that's a differential. Okay. This is a polynomial, so it is continuous and differentiable. I'm really not going to make you when you're working out your problems. I just want to make sure you're aware of it, because there are situations where this rule wouldn't apply. Okay, so as long as it's continuous and differentiable, all we have to do, the derivative is just going to be this function, but instead of t's, what will take their place? X. So it's just x squared plus 2x plus 1. And we're done. Now, to show you why that works, let's actually work it out. If I wanted the derivative of this integral, first I would have to actually do the antiderivative, wouldn't I? So if I wanted the antiderivative, t squared would go to 1/3 t cubed. 2t would go to t squared. Antiderivative of 1 would be t. And I'm going to evaluate that from 3 to x. So if I put in my x, I would get 1/3 x cubed plus x squared plus x minus, if I put in my 3, 1/3 times 27 will be 9 plus 9 plus 3. And so we get this function. That's our antiderivative. Now the original problem was to find the derivative of it. What's the derivative of this? X squared plus 2x plus 1. Just like we got before by the fundamental theorem. It has to do with the fact that when you evaluate it, the antiderivative and derivative are just going to undo each other. When you go to evaluate, your t's are going to become x's. The constant will give you a number, but when you do the derivative of that number, it will turn into 0. That's why this works out. Alright, any questions there? So let's just practice some. Let's find the derivative of this function. So we could work it all out. We could look, the square root exists as long as you're putting in positive numbers, right? And we are. In fact, in this case, it wouldn't even matter because it's t squared. It'll become positive anyway. So it's going to be continuous and differentiable on our interval. So we could just use the fundamental theorem of calculus. So using the fundamental theorem, what does it become? And that's it. There's no need to do all that work. So this was just the derivative. We could call that g prime of x if we wanted. The next one is a little bit different. I told you I wanted you to work this one out. Why can't I just use the fundamental theorem here? It's an x to the 4th, not an x squared. Okay, so let's work this out. If I wanted the antiderivative of 2t would be, minus the antiderivative of 3 from 1 x to the 4th. Okay, if we plug that in, we get x to the 4th squared would be x to the 8th minus 3x to the 4th minus, if I put in a 1, I get 1 minus 3. Okay, what is the derivative of this?
X to the 7th minus 4x to the 3rd.
So here's our derivative. Now, is there any way we could have got this by the fundamental theorem? Now, if this is just an x, we plug it in. It was an x to the 4th. If I just put an x to the 4th in the original, we would have a 2x to the 4th minus 3. That is not the answer that we got. How are these related? You took this times 4x cubed. Do you get what we have up here? Right. If you have x to the 4th, where could 4x cubed possibly come from? Derivative. It's like the chain rule. So if it's not just a plain x, you can essentially do the chain rule. Plug it in times the derivative of what you're putting in. Alright.
So that's will be like one of the that'll be the only time where they don't match, right?
Well, it would match if we multiplied by the derivative of it. So now that we know that, why don't you guys do 3D? I want the derivative of this one. Third. Because you plug in your x to the 4th, derivative of x to the 4th is 3x cubed. Not 3x cubed, 4x cubed. Okay, so the first part of the fundamental theorem is okay. You're doing the derivative of an integral, they essentially are just canceled. The second part of this, we've been doing these antiderivatives, we've already talked about that. This is just finally putting it in a theorem that to evaluate that integral, you can just do the antiderivative and subtract. That's giving us the area under a curve. So the second part we've already used. That isn't the new piece. It was just the first part that was new. So I just want to keep practicing these integrals. We had them on your test. We're going to keep having them the rest of the semester. So if I want the antiderivative from 1 to 3 of e to the x dx. What's the antiderivative of e to the x? Dx. We're evaluating from 1 to 3. So that's just e cubed minus e to the first, or just e. Okay. I might ask the question a little bit different. I might say find the area under the parabola y equals x squared from 0 to 1. Area under a curve is the same thing as an integral. So we're going to integrate from 0 to 1 of x squared, and what should I write at the end of that?
2x.
Yes, good. So my x squared will turn into 0 to 1. So we just get 1. Nothing new there. So if I asked you to do this one, what's that mean? Or is there another way I could rewrite it that might be useful? You could write this a couple different ways. This is like 1 over x dx, or x to the negative 1 dx. Those are all equivalent. What is the antiderivative? Natural log. So we get the natural log of 6 minus the natural log of 3. Alright, bonus points. Anyone tell me how to simplify that? No? Yes! You just made my day. If you have two logs subtracted, don't you remember you can put them together and divide? So natural log of 2 is the best answer. I probably would not count it wrong if you told me natural log of 6 minus natural log of 3, but I'd be really excited if you put natural log of 2.
Yeah, that's the best answer.
Disappointing. Alright, let's look at this one. Absolute values, your favorite. What do we have to do on absolute values? Break it up. We need to find out what makes it 0 so we know how to break it up. What could I pull out here? That's going to leave me with x squared minus 1. How do you break apart x squared minus 1? So this equals 0 at 0, negative 1, and positive 1. Yes, isn't that fun? Now, lucky for you, I guess, the negative 1 isn't really going to make an impact because that's where I'm starting. So we are going to have to integrate from negative 1 to 0 of something. Then we're going to have to integrate from 0 to 1 of something. And then we have to integrate from 1 to 2. Now I wrote too big. Okay. From 0 to 1. You can look at a graph, you could plug in a number. We need to figure out what the absolute value is going to do here. If you put in a negative 1/2, if you're not sure, you can always do negative 0.5 to the third minus negative 0.5. Does that give you a positive or a negative answer? Positive. So, does the absolute value change it in that scenario? If it's already positive, does absolute value do anything? No, so I'm going to keep this as x cubed minus x. Alright, if you put in a number between 0 and 1, so if you put in 1/2, positive or negative? Negative. So does the absolute value change it? It'll do the opposite. So can I write that as x minus x cubed? Is that confusing maybe? I just went ahead and distributed my negative. If you put in a number between 1 and 2, so like 1.5, is it positive? It's positive again, so we go back to the original. Absolute value isn't changing. So now we have 3 different integrals to do. So antiderivative of x cubed, -1 to 0. Okay. Then this is just going to flip, so it'll be 1/2 x squared minus 1/4 x to the 4th from 0 to 1. And then 0 minus if you put in a -1. We get a -1/4. Put in a 1. We get 11/4. I want h prime of x, given that h of x is the integral from 0 to x squared of t cubed sine t dt.
Okay, so plug the top one, like the derivative of the top one in.
Okay, so you'll have to, it's really a couple steps here. We know our derivative. We can do the fundamental theorem of calculus, right? If you plug in an x squared here, you get x squared cubed, which would be x to the 6th sine of x squared. But because it wasn't just a plain x, you also have to take all this times 2x. So we get 2x to the 7th sine of x squared. I think I can do one more and then I'll probably stop for today. This is really the last new type of problem in this section. So Tuesday I'll work through some of the last examples. They're really just review over the things that we've already done, and then you will have time to work on homework as well. Depending on how things go, I may start the next section at the end of class on Tuesday. We'll see. So express as an integral the solution to the initial value problem dy dx equals secant x y2 equals 3. So this one is different. I know this right here is telling me that the derivative is equal to secant of x. It's asking me to write an integral. Now, do we know a trig function that has a derivative of secant? No. So it's not just a nice one where I could say, you know, that we're it's not one that we know. So we can't just do the antiderivative of secant. But we can use the fundamental theorem of calculus. That says if you are doing the integral from a constant up to x of something, you just get to plug in the x at the end, right? So I don't know my constant yet. Let's just wait on that. If this is an x, we wouldn't want to put an x here yet. What have we been seeing? T. Okay, so as long as this is a constant value down here, then if I did the derivative of this, it would just be secant x, which is what I want. This is telling me something that has to be true. Y of 2 is equal to 3. If we want to make our problem as easy as possible, let's make this constant the same as the constant here. So let's do the integral from 2 to x. Okay, so far the first requirement is still met. The derivative of this is secant x. Y of 2 equals 3. It's saying when I plug a 2 in for x in this problem, I have to get 3 for my answer. If I put in a 2 for your x, this is a property about integrals that I gave you at the very beginning and we haven't really used since. if you integrate from 2 to 2, this whole thing would turn into 0. We could have a constant value out here as well, right? We know if we do the derivative, the constant would disappear. And we want this whole thing to equal 3. So this would be 0 plus my constant equals 3, so the c has to be 3. So the actual solution to my initial value problem here is this. We were doing initial value problems, there's even one on your test, where you had to do the antiderivative and actually find your c value. That's what we're doing here. This is the derivative. When you do the antiderivative, you can have a plus c on the end. We found our c value by using this point. And this worked out because I made my constant, my function, start at 2 and go up. If I hadn't put a 2 here, it would have been a lot harder. If I put a 0 or something, then I wouldn't have been able to just say that goes to 0. So that's why I picked 2 as my starting point. And then it meets both requirements. Any questions? We will do more of this.